Okay, so we've got some basic problems here dealing with simplifying exponents. So the instruction is to simplify or solve, in this case, for a, for each of these problems. So let's find the value of a in each of these using our laws of exponents. First, we have 3 to the a times 3 to the fourth equals 3 to the 12th. Well, remember, one basic law of exponents is that if you're multiplying two values, any two values, as long as the base is the same, right, the number that's being raised to a power, right, x to the a times, let's say, x to the b, what you would do then is what? Well, you'd add the exponents. This is equivalent. So this comes from the idea, of course, of the commutative and associative properties, which we can show with this problem. But first, let's quickly solve it. So if we have 3 to the a, let me use a different color, 3 to the a times 3 to the fourth. So I'll use little x's for times. I use a dot up here, but there are x's typed out here, so I'll work with that. So 3 to the a times 3 to the fourth equals 3 to the 12th. Well, what we would do here is think, okay, well, I know that if I add these two exponents, I should get 12. So I might set up a little algebra equation that a plus 4 equals 12, and solve for a by subtracting 4 from both sides. What happens now is that 4 cancels out, and 12 minus 4 is 8, so a is equal to 8. And that makes sense. If we kind of plug this back into our formula and rewrite it, we have 3 to the 8th now, because that's the a value, times 3 to the 4th, and when we follow our laws of exponents, we add 8 and 4 to get 3 to the 12th. And again, just to show you this idea is, well, 3 to the 8th, if we think about that, that means 3, right, times itself 8 times. So there's 8 3's there. Oops, I wrote an 8, right? 3 times itself 8 times. And then we're taking that and multiplying it by 3 to the 4th. So 3 times 3, 4 times. And if you look at this operation, you might realize, okay, all we're really doing is multiplying 8 3's over here and 4 3's over there. So if we group them all together using our commutative and associative properties and rearrange as we need to, although I guess here we could just regroup and use the associative property, what would happen? Well, 8 3's and 4 more would give us a total of 12 3's, all grouped together and all being multiplied, and that is 3 to the 12th. So in fact, that's kind of the idea here. You're just adding the number of 3's that you're multiplying to get the total number of 3's that you're multiplying. And it carries over right into the next problem, which says, well, 4 to the 6th times 4 to the a is equal to 4 to the negative 4th. Now, negative exponents, remember, just mean division. In this case, 4 to the negative 4th would mean 1 divided by 4 times. So we're not getting a negative number here, but we're still following the same basic principle that, in this case, 6 plus a is equal to negative 4. So solving for a, what happens? Well, if you think about the addition of negative numbers, you have to add some amount to 6 that gives us a negative 4. So if I subtract 6 from both sides, I can quickly figure out, this cancels out, that a is equal to negative 10. And that makes sense. You have 6, you take 10 away, and that gives you negative 4, the exponent we need. So we'll keep going here, and we run into our second, well, depending on how you number these laws of exponents, another law of exponents. This law here deals with the idea of raising a power to a power. So maybe x to the a power, right, to the b power. And what we're going to be doing here is multiplying the exponents. And this just builds off of the law we showed up here, and I'll kind of explain the connection in a moment. But here, to solve, of course, this means that 3 to the second power to a, if it equals 3 to the 24th, well, that means we have to multiply our exponents here. We have to multiply 2 and a to get 24. So 2 times a is equal to 24. If I divide both sides by 2, a is equal to 12, right? Because 2 times 12 is 24. So here the answer is 12, excuse me. So this idea is just showing the fact that when you raise a power to a power, you're just repeating the multiplication of the same base to some power over and over again. So in this case, we have 3 squared, right, to the 12th power. What does that mean? Well, don't rush to evaluate 3 squared and say that's 9 and this is 9 to the 12th. That's not wrong, but we want to look for a structure here in the exponents. And what I mean is, when you raise something to the 12th power, whatever's inside those brackets, whether it's 3 squared or any other number, of course that means you're multiplying what's inside these brackets 12 times. So in this case we'll have 3 squared, right, times 3 squared over and over and over again 12 times. So if we think about what this means is we have 12, right, 3 squareds. And if we follow our laws of exponents, we're going to add these exponents over and over again. So we're going to add 2, right? How many times? Well, there are 12 of them, so we're going to add 12 times. Adding 2 12 times is the same as multiplying 2 by 12, which is what we're doing right here. So there's some logic there in multiplying these exponents that connects right back to the very first law we mentioned in these exercises. Now what's nice is that when we multiply and the base is equal, we add the exponents. Well, what's so wonderful about the way we set up the law, or the way we use the laws of exponents, I should say, is that multiplication and division do behave like inverses. So what does that mean? Well, if we add exponents when we multiply, right? So x to the a times x to the b, that equals x to the a plus b. Then, and I love this, it just fits so nicely, if we divide, right, x to the a divided by x to the b, then we subtract the exponents. There's certainly a magnificent, I think, simplicity there, right? Multiplying and division are opposites, or inverse operations, excuse me. So then it makes sense. The inverse operations of addition and subtraction help you understand the shortcuts in these laws of exponents. And not only does it fit nicely, but there is a simple logic to it, which we'll get to in this problem. So we have 2 to the 10th divided by 2 to the 3rd. If I rewrite that as a fraction, that means 2 times 2 times 2, right? 10 times, that's 2 to the 10th, over 2 to the 3rd. Well, the logic here is that every time you have a 2 in the numerator and denominator, they divide to 1 and cancel out. They're not going to impact your answer. So notice, because this is 2 to the 3rd, there will be 3 2's, right, to cancel out 3 of the 2's from 2 to the 10th. So it's like subtracting, because we're subtracting out the products, the factors that will cancel out. So we subtract the 3 2's here from the 10. It tells you how many 2's are not canceled out, how many are left over. In this case, there are 7 2's left over. So the answer then is 2 to the 7th, right? 2 to the 10 minus 3. And moving on, here we kind of encounter maybe a more confusing law of exponents, but it builds off of this idea that if you have the product of terms to a power, right, you can actually raise each term to the power and multiply to get the same answer. So if we have x times y to some power, we can take x and raise it to the a power, or whatever power it is, and y to the a power, multiply them, and we'll get the same answer. So how does this play out in a problem like this? Well, we have negative 3, right, times d squared times y to the negative 3rd to the a power. And we know that it equals negative 27 times d to the 6th times y to the 9th. Well, my key in solving this problem is looking at the coefficients. It just helps me out, right? We have negative 3 and negative 27. So I think to myself, well, if I have negative 3, what power do I have to raise it to? Right? We're trying to find the a power to get a negative 27, right? Because we know the law of exponents here is telling us that if these two things are equal, right, we can apply this exponent to each piece, each term inside the parentheses. So we're going to raise negative 3 to some power, and that's how we got negative 27. So what will do that? Well, if a is equal to 3, that means what? Well, we have negative 3 to the 3rd power, which is equal to negative 3 times negative 3, that's positive 9, times negative 3, and that's negative 27. So we basically solve it here because now you know the exponent is 3, right? A is equal to 3, and we can test it out because then we would cube d squared, and d squared cubed, we multiply those exponents just like before, is d to the 6th, which we get, and then y to the negative 3rd, right, cubed, is going to equal y to the negative 9th, right? Negative 3 times 3 is negative 9, and that's what we have here. So here the exponent a is equal to 3. Just be careful, of course, you can't distribute an exponent if what you have inside the parentheses is either a sum or a difference, right? X plus or minus y to the a power does not equal x to the a plus or minus y to the a. You can only really kind of, I guess, in a sense, distribute this exponent to each piece if multiplication is the operation. And we'll talk more about why in other videos. All right, thanks.